All right, here's part 2 of the review. Let's see, we have a problem here with a table of data about the height of a hot air balloon after a few seconds, and it wants us to find the slope, find the y-intercept, and write the slope-intercept form of the equation. Let's see. Well, to find slope, we got a couple different ways we could do that. We could use the slope formula, which would be m equals y2 minus y1 over x2 minus x1. So then we could pick any of the 2 points and plug that into the formula and find the slope there. Or if we're thinking here, let's think about, what is slope? It's the change in the y values, which in this case would be the height of the balloon, because that would be dependent on the time that's passed. So notice that's adding 9 there, and it's adding 9, it's adding 9. So we see that pattern of adding 9, and then the x values, what's the change there? So that's plus 1 and plus 1 and plus 1. So the change in y over the change in x would equal 9 over 1. So there's a faster way to find the slope. So our slope is 9, or 9 over 1. And so then it wants us to interpret that. So what we want to do is think about what's the 9 represent. So the 9 was our change in y values, and so that's about the height of the balloon. So that's 9 feet. And we use the word per, or each, or every for the line. So 9 feet per. And then what's the x values about? It's time. So seconds, 9 feet per 1 second. So, and then this balloon is rising or increasing. Like the height is going up each time, each interval. So we want to make sure we use a word like that in our interpretation. So the meaning is the balloon is rising, climbing, anything like that, some sort of positive word, as opposed to if the balloon is falling or descending, it would be a negative word. So we want to make sure we include that here. 9 feet per second. So there's our interpretation. All right, so to find the y-intercept, so we could go into point slope form, and then use that point slope form and turn it into slope intercept form, which would then have the y-intercept, which basically would be answering part C right now. So we can go and do that, because now we know the slope and we know lots of points that we could use as our x1 and our y1. Oh, excuse me. Or if we think about it, right, what we know about all y-intercepts is that their x value needs to be 0. Well, look at our x values that we have. We have 1, 2, 3, and 4. So if we can imagine going back in time 1 second, right, up to 0 seconds, that if we could go back in time 1 second, so minusing 1, then if we went back in height, that would be minusing 9. So 12 minus 9 would be 3. And so our y-intercept would be 3. So there's a different way to do it. Since we have some data, you can do that. So we know our y-intercept, and again, the idea that we want to think about what those numbers stand for. So the 0 is our x, which again was seconds, and then the 3 was height or feet. So at 0 seconds, there is 3 feet. So remember, we don't say 0 seconds, we say something like beginning or starting or initial. So the initial height of the balloon was 3 feet off the ground, or the balloon began 3 feet off the ground, so something like that. Or the balloon started 3 feet off the ground. So there's an interpretation of that. Again, we could, for part C, we could plug values into the point slope form and get all that, or we could just take what we know now, that we know our slope is 9, and so 9x, and then we know our y-intercept is 3, so we just write that. So there's our slope-intercept form of the equation, y equals 9x plus 3. And then after how long will the balloon be at the height of 80, or after how long will the balloon be at a height of 81 feet? So 81 feet being a y value, we would plug that in for y. So 81 equals y, oops, not y, 9x plus 3. We're going to solve for x. So minus 3, so 78 equals 9x. So divide by 9, and you end up with x equals, let's see, 78 divided by 9, 8.66, so 8.6 repeating. I feel pretty safe saying that we could round this. There's nothing here saying that we can, anything about rounding, but we wouldn't be able to tell the difference between 8.6 seconds and 9 seconds. If we're just, it's not something that we're really capable of doing. So I'd say, after, about, or around. So as long as you use one of those words that's saying that you're saying it, you're estimating. So after around, or after about, or after approximately, then you're okay saying that, since there was no given specification about how much to round to. So after around 9 seconds. Again, just also thinking about what we are capable of discerning, So, alright, so there's that problem. Next one's pretty similar in what it wants us to do: find slope, find y-intercept, write equation, then use our equation to do something. But this time they're giving us a graph to use instead of just a table. I'm going to start the same way, so I could use the slope formula to find the difference in my y's, and then my difference of my x's, or I could just look at my look at my graph here. And so if I say, what is the difference in y's, what is my rise for this problem, that'd be, it's going up 30, and then I look at those x values and how they're changing. It's going up 75. So I want to do slope equals the rise, the y values change over the x value change. So 30 over 75, which reduces down to 2/5. So what does that mean, right? So what does y stand for? So that's because our 2 is 2 in the y direction, so that's 2 megabytes. And then what does x stand for? It's time in seconds, so 5 seconds. And then so we have 2 megabytes per 5 seconds. So what does it mean? Looks like we're talking about something downloaded, so we download 2 megabytes every 5 seconds. Alright, and the y-intercept. So we have the graph here, but if we notice, the graph has a break in it, so that in the x-axis. So just trying to extend the line down is not going to be okay because of this break. So I can't really do that. So I'm going to have to go ahead and do the point slope form. So y minus, and I pick one of my y values, so I'll just use this point. So y minus 10 equals, and then I have my slope, which was 2/5, and then x minus, and then my x value of there was 25. So then distributing the 2/5, so I get y minus 10 equals 2/5 x, and then 2/5 times 25, or it's 25 over 1, so it'll be 50 over 5, which is 10, so minus 10. And then getting that y by itself by adding 10 to both sides. So we end up with y equals 2/5 x, because the 10s cancel each other. So that means our y-intercept is 0. Of course, we don't need to write that. So if the x value is 0, it means our y value is also 0, since our y-intercept is 0. So how do we interpret that? So again, what does the x value stand for? That's the time, so 0 seconds. And then our our y value is how many megabytes do we download. And it actually should make sense, right? If we don't spend any time downloading, then we should get 0 megs downloaded. Or at the beginning of this process, we have 0 megabytes downloaded already, so should kind of make sense though. So 0 megabytes downloaded at the beginning or at the start. That's our interpretation there. And then we just wrote the equation in slope intercept form already, so don't need to worry about that. Let me fix this real quick. And then use the find the file size. It took 75 seconds to complete, so seconds is an x value. So I'm going to plug this 75 in for x. So y equals 2/5 times 75. 2/5 times 75 is 30. So that would be 30 megabytes. All right, that page is done. Moving on to the next one. All right, these are pretty easy. Most of it's already been done for you. It's just remembering this what we did here. So we got all this data. Here we have something about odometer reading in a car versus its trade-in value. They've already put all the data into Desmos and gotten all the numbers out over here like we saw when we did it. They want us to write the slope-intercept form of the equation, so that's going to use the m value here and the b value here. So I'm just going to write y equals m. So I'm not going to do any rounding. I'm just going to go ahead and use the numbers like they are. X plus, and then 34814.5. So there's my equation. That's pretty easy. So this, that. And then find the trade-in value with an odometer reading of 35,000 miles. So odometer reading here was our x value. So that's going to be plugged in for x. So y equals negative 0.181435000 plus. So be really careful as you type in that calculator. There's a lot of numbers there. I know when I was doing this the first time I made a mistake in my typing, and it was really hard to find that mistake. I was really confused about the answer I was getting for quite a while until I finally found that little tiny mistake. And of course that can be frustrating. So that gives me 28474.6, but we know this is money we're talking about here, so I should say 60. So the trade-in value would be $28,474.60. And then the last thing they want us to do is to interpret the correlation coefficient, there we go, which is just R. So what is it? What's it mean? So R equals, don't use R squared, use just R, 994. So this has to do with that chart we had that one day where it started at -1, went all the way to +1, and then 0 in the middle. And those numbers, those values near 0 were weak, whether they were weak positive or weak negative. In between there was moderate negative or moderate positive, and then as we get closer and closer to 1, those were the strong correlations. So this number is really close to -1, so this is a strong negative correlation. So we would just say there is a strong negative correlation between, and just go back to your chart and look at the variables. What are we talking about here? And so one of the variables is the odometer reading, which just means how many miles are on the car. And the other variable is the trade-in value. So should make sense. The more miles you have on your car, the less it is worth. So as one thing is increasing, the other is decreasing. That's why it's a negative relationship. Okay, so that was pretty simple. This table is showing us values for year, what year it is, and then how many millions of dollars of tickets were sold at Broadway. So same thing here. We're just going to take our slope and our y-intercept and write our equation. So, whoops. So y equals, so my m value is 52.922 x plus, oops, that's minus 105,260. All right, so there's my equation. Pretty easy. Find the expected sales in 2010. So again, the year was our x values. So I'm going to plug in 2010 into x. So y equals 529,222 times 2010 minus 105,260. Alright, so that gives me 1113.62. Now they don't have any decimals here, so 1113.62. So they haven't used any decimals in their y value, so I'm going to go ahead and round this up. 1114. So that's in dollars, and it's also in millions. So 1,000 millions is actually a billion, so this would be $1.114 billion, but it's fine if you leave it in millions. So just thinking about what it means, though. It's over $1 billion in sales. And the last thing I want us to do is interpret that R value again. So our R value, is 0.9. So R equals 0.98. Since they did ask us to state it, I'm going to state it and then interpret it. So again, that's really close to 1, so that's a strong correlation. It's positive, so it's a strong positive correlation. So strong, oops. So there is a strong positive. We're not going to give you any tricky numbers like, oh, what does it mean if it's 0.39 or something like that? They'll be pretty obvious, like it's going to be strong, or it's going to be a strong one like 0.9, or it's going to be a weak one like 0.1 or something like that. So strong positive correlation between. So then go back to your variables. So the first variable was what year it is. And the second variable was the sales, ticket sales on Broadway. And what that means, since it's a strong positive, is that a year goes up, the ticket sales would also go up. And it's strong because there's a very obvious relationship between them. So, all right, that's the 5th page. Here we'll move on to the last page. So we have more of the applications of compositions, and this first one is definitely a really kind of confusing problem to talk about. We don't really talk about concrete foundations and areas of tanks, bottoms of tanks very much. So it's hard to talk about, but the math is pretty simple for this one. And then, oddly enough, the last problem, I think it's much easier to talk about, whereas the math is more difficult. So, and you guys don't need to worry, like the math on number 42 is quite a bit more complex than anything we're going to ask you guys to do. But just kind of use it as practice. So you're reading that problem. So we had a concrete foundation. It sits on for a cylindrical tank. It says the radius is a function of the side length. So here's this radius function. So I'm just going to highlight that there. And then the area of the circle is a function of the radius. So we've seen radius mentioned twice. And they give us another function here. So a of r equals this. They want us to find a of r of x. So remember what that means is that we want to plug r into a. So we're going to take this r function, and it's going to replace the variable in a. So I would say that's 3.14 times something that's being squared, right? And that something is 0.5x. So we need to think about simplifying this. Remember, you're following PEMDAS, so you should do this exponent before the multiplication. So we need to square 0.5x. So 0.5x times 0.5x. Well, 0.5 times 0.5, a half of a half is a fourth, so 0.25. And then x times x is x squared. So I get 3.14 times 0.25x squared. I need to figure out what 0.25 times 3.14 is. That's 0.785. So that gives me 0.785x squared. So that is what a of r of x equals. It says now interpret its meaning in context. So this one's hard to talk about, like I said. I'm not used to talking about concrete foundation areas and the area of the bottom of a cylindrical tank. It's not something I'm familiar with or comfortable talking about, so it's harder to describe what this means. But remember that outside letter is what the function gives us. In this case, there's not really an outside, but it's the first letter. So this function is going to give us the area of the circle. Okay, because that's what A tells us. So it's the area of this circle, it's the area of this base of this tank being determined by, and then that last letter x, the one that's the input, which is the side length of the square concrete foundation. So, so this function tells us the area, and you guys don't really need to worry about writing this down or understand this too much, but of the cylindrical area of the base of the cylinder, base of the cylinder, as a function of the side length of the square. Square, I don't know, foundation or something like that. If you think back to question 26, it had a really easy interpretation, and number 42 also has a really easy interpretation to understand, so I wouldn't worry too much about something crazy like this. They do want us to find a sub r of 10, or a of r of 10. So I'm just going to plug, 10 is what my x should be, so 0.785 times 10 squared. Again, do the exponent first, so 10 squared, so 0.785 times 100. Or multiplying by 100 just moves a decimal twice to the right, so that'd be 78.5. Okay, well, so we are plugging in 10, which stood for the side length of the square. So if the side of the square is 10, and then it gives us out A, which is the area of the cylinder, or the base of the cylinder. So again, you guys don't need to worry about this interpretation. If the foundation has a length of 10, they never told us like units, so if it's feet or whatever, they would just have to say 10 units. then the cylinder, cylinder's base would have an area of 78.5 units squared, so feet squared, inches squared, whatever. But we just know it's units squared. So again, don't worry about having a really complicated explanation like that. So it'll be much simpler on the test and like this next problem. So, all right, so another composition of function application. So again, we got some bacteria and food given by this. So the number of bacteria based on the temperature of the food, so N of T. When the food is removed from the refrigeration, the temperature if the food is given by, so here's a T of T, so that's a little weird, but the big T being temperature, the little t being time. So I've got a function that's talking about the number of bacteria based on its temperature. We've got another function I'm talking about the temperature of the food based on how much time it's been out of the refrigerator. And they want me to find N of T. So notice that the N is on the outside, so that means we should be plugging this other function into N. So it's going to take the place, so it's going to take the place of the big T's here. So it does have to go into both places where there's a T. So I said the math on this problem is more difficult than the math on the other one. And again, it's more difficult than you really need to be worried about. We're just going to do it just to get some practice. So that would be 10 times 3t plus 2 squared, and then minus 20. So then we replace another t, so 3t plus 2, and then plus 600. So this looks kind of like weird here. So fix that. 3t and then a plus. So I need to do a bunch of simplifying here. I'm not going to spend time talking about it because you guys should be able to do it on your own, but the first thing we need to do is square the 3t plus 2. So that means 3t plus 2 times 3t plus 2, and go through the the whole foiling process to really look like this. And when you do that, you end up with 9t squared plus 12t plus 4. And then the 10's there, minus 20. Plus 600. And then we got to do some distribution of the 10. So doing that gives me 90t squared plus 20t plus 40. Distribute the negative 20 would give me negative 60t, and then minus 40, and plus 600. So combining some like terms, I've got some t terms I need to combine. I've also got some just constant terms I need to combine. And if you notice, the plus 40 and the minus 40 are just going to cancel each other. Almost done. So we get n of t equals, so 90t squared. 120t minus 60t would be 60t positive. And the only thing left we had was the 600 as far as numbers go, so plus 600. So there's our n of t function. What does it mean? So the outside letter is what gives us, so that's the number of bacteria. The inside letter is what it's based on, so the number, and that was time. It's the number of bacteria based on time that the food is out of the refrigerator. So something easier to talk about, something probably a little bit more familiar to you based on the time. The food is out of the refrigerator. Okay. And then they want us to do a little bit of math here. So they said Little t is 2. All right, so that's what that means. So I'm going to plug in, and every t here is going to get a 2. So these spots over here. So that's going to be 90 times something squared plus 60 times something plus 600. And that something is a 2. So 2 squared is 4, so I get 90 times 4 plus 60 times 2 plus 600. 90 times 4 is 360 plus 60 times 2, which is 120, plus 600. 360 plus 120 is 480, plus 600 is 1080. So there's my n of t of 2, 1080. So what does that mean? So how do I interpret that? So remember, what it spits out is the outside letter, so it's the number of bacteria. So this is the number of bacteria based off of this inside number, which was 2 hours. So if the food is out of the refrigerator for 2 hours, there will be 1080 bacteria on it. Alright, and that's the last problem of the review. Hopefully this helped. I know it's not a great situation for me not to be there when you're supposed to be able to talk to me and ask questions, but hopefully this is a decent replacement, and hopefully the part you take on Thursday goes well, and I'll really hope to be back on Friday. Hope my daughter's better, so good luck and take care.